Right, let's resume this video about differentiation. So first of all, I'd like to make a couple of remark corrections and let's say suggestion for let's say adjusting the proof I've given previously, the proof of the general. The first thing I would like to point out that I said something silly when I was differentiating g of x. G of x equal x times square root of absolute value of x, which is the function defined everywhere, continuous everywhere on R. This is not so hard to verify. The derivative at 0 is vanishing. Well, this is easy to see. I already have said that was correct. But what was not correct is that the derivative at any point except x equals 0, because g prime at 0 equals 0, it has to be computed separately. Well, we have square root of absolute value of x and then plus sine of x. So it depends, the sign of this part depends upon the sign of x. If x is positive, this is a plus sign. If x is negative, it's a negative sign. I forgot to tell you this. Sorry about that. But this being said, now there's one thing I would like to say about the statement I said, that g prime plus epsilon and h, where epsilon and h is a function that tends to 0 when h tends to 0, is bounded by 2g prime of x plus 1. Actually, I don't need the factor 2. G prime plus 1 is enough. That's not so hard. How do we show this? Well, it's sufficient to choose h sufficiently small. So I take that's what I said. There exists an HGO positive such that if h in absolute value is less than HGO, so h sufficiently small, that means the same thing. Well, epsilon on h in absolute value is less than 1. That's enough. And if this less than 1, what do we have? We have g prime of the absolute value of the sum is less than the sum of the absolute value. And g prime of x is a number. It doesn't change because we are looking at the chain rule, that is the derivative of the composition with, of f with g. I think it was g composed with f actually, in that order. So we need to give a bound that doesn't depend upon h. It may depend upon x, but since x doesn't change, this is a uniform bound, in other words. All right, so this essentially ends what I wanted to say about the former video. Now, you may complain one thing about the last video. I talk about the derivative of sum, the derivative of product, the derivative of the composition, but I didn't recall the quotient rule. Well, actually, this is something that we can do without really taking two functions f and g and looking at f of g at x plus h minus f of g and divide by h or when not. I mean, you can do this, of course. This is exactly what Rosenlich does in this book, but actually there is a, well, I would not say a smarter way, but a lazier way to do that. First of all, I'm going to ask you guys to it's an easy exercise to retrieve the derivative of h of x. So it is typically an exercise that we can still give in calculus 1, so it's not so hard. And of course, you perfectly know that the derivative of the harmonic function 1 over x, as long as x is different from 0, that's important, is minus 1 over x squared. So I let you do this exercise, and once you have done this, I have the following corollary. Assume g is a differentiable function defined in an open set, and g of x is different than 0. Then I said that the function 1 over g is also differentiable at this point x, and actually everywhere in u where g of x is different from 0. And thanks to the chain rule, I can say that 1 over g of x is just the composition of h we have computed here with g. Nothing else. Then computing this is nothing else than as I said. So you look at the derivative of h, which is 1 over its input, and its input should be at g of x times the derivative of g prime of x. So you get exactly this formula. So this is nothing else than the formula of the quotient rule when the top is a constant equal to 1. Then how do you get the general quotient rule f over G? Well, you just said that it's the product of 1 over G times F. Well, you still need to make sure that G doesn't vanish at the point we are differentiating. But then if you look at the product rule together with this new rule, well, this is something that I'm sure you have done many times when you in ancient time. So F divided by G, I say at X is nothing else than F of X multiplied by 1 over G. Now, if I want to differentiate this, I just said this is F prime at X times G of X, and 1 over G of X, I should say, plus F of X times the derivative of 1 over G of X, but now we know that it's minus F of X divided by, multiplied by G prime of X divided by G square of X. Alright, since G of X is supposed not to vanish, you can look at this part here and multiply by G of X both guys, and this is pretty much the quotient rule you have learned from calculus 1. So this complete absolutely all the let's say the formula, pretty much the formula that you learn in calculus 1. Well, all not exactly. Actually, there are a couple that you can also quickly revisit. So I will discuss this with you. This is a proposition. We need to know how to differentiate polynomial, yeah, because as I've seen Stone-Weierstrass, as I said, they play an important role in analysis. So we like to know how to differentiate those functions at least. So what is the derivative of x to the power n when n is an integer? Well, you could definitively do it by hand and look at x plus h to the power n minus x to the power n and divide by h. Look at the limit when h tends to 0. There's many ways to do that, but there's also a lazy way to do that. It's just by induction. Let's show when n equals 1. What is x prime? Well, you know what it says, the limit as h tends to 0 of x plus h minus x divided by h, and of course this is 1. That's easy. You assume that the formula is quite known for a certain rank n, for all x belonging to R, and for all n less or equal than p. Let's show that it's still true for the next integer. So what is x to the power p plus 1? To be differentiated, this is x to the power p times x differentiated. So this is equal to, now I'm going to use the induction property because this is true up to n equal p, so it's p times x to the power p minus 1 times x plus x to the power p times the derivative of x, which is 1. And you know, well, you just count this, so this is equal to x to the power p times p plus 1. And this means that this formula is still true for the next integer. So it's true for any integer. So that's easy. Exercise, and using the trick I've shown you here with the inverse function. So exercise, show that xn differentiated equal n xn minus 1 also when n, if n belongs to z. That's what I wanted to say. For all x belonging to R, yeah, so minus the origin, I want to say, and for all n negative, I want to say this is better. Yeah. Actually, we could go even further. You can even, by using again this power rule here and the composition, you could show that if you replace n by any rational, this formula is still true indeed, right? Making sure, of course, that sometime when you subtract one, you can go from a power which is positive to a power negative, for example. That's the case when you take the square root of x, right? Well, okay. There's a lot of things, there's a lot of, let's say, elementary exercise where you could retrieve pretty much the derivative of all functions, analytic functions that you have encountered so far since Calculus 1. And this is not, let's say, the spirit of this course. So now, what is the spirit of this video, of this module, of this course? The idea is how to reconstruct pretty much, not that we are starving to reconstruct the theory, but how to reconstruct the theory of differentiation by the use of the theory of underneath metric space and topology you have learned before, and you will see that a lot of things will just drop 1 to 3. The next theorem I like to talk about is something that you know, but it's some have a tendency to be neglected by a lot of students in Law division. Let me say this, so don't take this personal, for sure not. So this is the Rolle theorem. And you will see that from Rolle theorem, a lot of other theorem will just follow. All right, so what is the thing? Assume f is defined on an interval AB and take its range. So both AB, so B is bigger than A, for sure. Take its range in R. F is continuous. We further assume that f is differentiable on the same set, except that it may not be differentiable at A and may not be differentiable at B. Well, for the simple reason here, actually, as I said earlier, I'm not so sure if I really know how to differentiate at the boundary of an interval. I mean, I can differentiate on the right for A, on the left for B, but not the full derivative. But say I don't. This is the magic of this theorem. I don't need f to be differentiable at A, not at B. Assume. So this is the next assumption. F of A and f of B are the same at the boundary. The conclusion, you know it, I'm sure. There exists a C strictly in the interval AB, such that f prime of C equals 0. So in other words, we like to say that C is a critical point. So since it's the first time that I speak about critical point in this type of video, I like to make it in full letter. C is a critical point. Obviously, when I say there exists, this is not necessarily unique. So the picture we should have in mind is pretty much this one. Take a graph of a continuous function between A and B, which is differentiable in between. The idea, it goes here, it goes there, it has to go back there. And yes, I can see there's a couple of points here for which the derivative vanish. Slope, in other words, the average rate, the instantaneous rate of growth of the function at those points vanish. Well, I mean, this is intuitive, this is heuristic, this is probably some sort of argument that we explain in Calculus 1 or in even higher division, and it should be, let's say, fair enough for a student to understand the entire game. But here we like to be more rigorous, of course. We can't accept to be too sloppy. All right, so how are we going to prove it? So first of all, proof. Let's say I'm going to assume that f is not a constant. That is, f is not identically equal to f of A, because f is already equal to f of A, which is equal to f of B at the boundary. I don't want the function to be constant. Why? Well, because if the function is constant, that's clear. The function is constant, the derivative of the constant is 0. This is something that actually I haven't said, but you can read the details in the book. I'm you don't need to read much, you know how to differentiate a constant. This is something quite clear, guys. I don't want to, let's say, waste your time by stating things that you can do easily by yourself. And when I say easily, I say very easy. So I'm going to assume that f is not constant. All right, so if f is not constant, f, therefore, f admits a supremum and an infimum so I mean, if I stop the sentence here, I mean, this was also true in the case where f was a constant. But in the case where f is a constant, the infimum and the supremum are the same thing, the constant. So in the case this is not a constant, one of them, I don't know which one, either the sup, either the infimum, is different than f of a. And of course different than f of b, because f of a was. Alright, so without loss of generality, I'm going to assume this is the supremum, which is different than f of a. If it was the infimum, which was, it could be that the function, the graph function looks like this, and this is pretty much the point under consideration we will be looking at. Well, if it's in the case, I still want to speak about the supremum of f, then you change f by minus f. So that's what I'm saying is, without loss of generality, I can assume that the sup of f of x when x belongs to the interval AB is different than f of a. Otherwise, well, consider minus f instead. Minus f will satisfy instead. Sorry. I mean, minus f satisfies the same property. Minus f is differentiable. Minus f of a equals minus f of b. And the conclusion will tell me that there will be a C such that minus f prime of c equals 0. That will tell me that there will be a critical point for f and also for minus f. So, quickly, here, this is the crucial part actually. This is the heart of the theorem, which after that will give the mean value theorem. This is where we stand, exactly where we stand. How can I say that the supremum of f, first of all, exists and is reached, and I can tell you is reached at a specific point? This is the thing. Well, I'm looking at the image of an interval which is closed and bounded. Closed and bounded means compact. The image of a compact set is compact. So I need to erase something here. So of course, if it is different than f of a, it has to be bigger than f of a. Yeah, well. So f of AB is a compact set. I can even say that since AB is an interval, the image of AB is an interval. That's also true. So it's actually, it should be an interval of the form CD, where both C and D are included in the interval. But I claim I don't need that. I don't need this to be an interval. This means what? This means that, so let's call this set K. Then the supremum of K belongs to K. This means that sup of K equal f of a certain point, C, where C is between B and A. Why can't it be at A and B? Well, we have assumed that the supremum of f on this interval is bigger than f of A. So the supremum will not be reached at f of A, nor at f of, it won't be reached at A, and it won't be reached at B. So it has to be at a point in between. The fact that supremum of K contains, so belongs to K, sorry, belongs to K, so this is a real number, this is a set, right? So the least upper bound of this set is in the set. Why? Because the set is closed indeed. That's what it takes, right? So maybe it may not be completely evident. This is something I realize I may not have time to spend some time on this, so maybe I'll stipulate this lemma. Let K included in R a compact set. Then let's call it, I'm going to call it M equal the supremum of K belongs to K. Well, that's, I could left it in as an exercise, but I want to be complete. First of all, is this supremum exist? Yes, because K is a compact set, so it's bounded. Bounded means that it admits a supremum. Okay, so M exists, but does it belong to K? Well, let's look at the characteristic of the supremum. For all epsilon positive, there exists X belong to K such that X does not exceed M, or sure not, but is bigger than M minus epsilon. Okay, well, let's take epsilon equal 1 over n, right? So this means that for any n belonging to n, there exists x equal xn, so I construct a sequence of points such that m minus 1 over n is less than xn, is less than m. Conclusion, xn converge to m, but it's a sequence in a compact set which is sequentially compact. So xn converges for a subsequence. Subsequence, that's the way I write subsequence. And this subsequence converge in K, of course. But xn is already something converging. So any subsequence of a sequence converging converge to the same limit. So here it tells me that I have a limit, it may not be in K. If it tells me it's a subsequence that I have, which for sure converge in K. Well, by gluing those things together, it tells me that not only the limit exists, but it exists in K. Alright, so this being said, this tells me exactly that the supremum of K is in K indeed, and that means that it is reached by a point through F. Alright, now let's see. Since F is differentiable at C, yes, remember, F may not be differentiable at A, may not be differentiable at B, so not at A, not at B, so I have to pay attention when I make motion with my hands, the left is your right, the right is your left. F is differentiable at C, yes, because C is in the interior, since C is in the interior of the interval. So if prime of C exists, and let's compute this derivative. So now I need to erase pretty much everything because this was a lemma which I should have said this lemma much earlier, and probably I should have said it as an exercise. It's an easy exercise. You see, it's done in essentially 4 lines on my board. It's not so long. Here, this is the key part of the theorem. I insist again, so I want to take my time and I want to separate, let's say, this theorem because it's really, it was quite a frustration for me when I saw the proof the very first time. When I read the theorem, it tells me it has to do with the derivative, And actually, no, it has nothing with a derivative. This theorem is a theorem in topology, not about the derivative. You will see that the part of derivative is almost trivial. So the part which is not trivial is saying that the image of a compact set is compact. Some say, well, the image of an interval is an interval. Yes, but you want also this interval to be closed and bounded. That's important. And compact here is the right word. You don't need to know that actually the entire set is the entire image in the interval. You don't need to know this, although it is true for sure. So again, as I said, not only it's a compact set, but it is indeed an interval of a form M, capital M, where M is the infimum of f on that set, which is also reached at a certain point, different than C, obviously. Otherwise, that will mean the function is constant. It is something that I wanted to avoid in the first place. And M, as I said, is also reached by a point which I call precisely C. So I could have taken also the infimum. So I take either the infimum, either the supremum. I just prefer to take the supremum. That's all. Even if I have to change f in minus. Okay. So this being said, here observe one thing. All what I said, I insist a bit. But all I said has nothing to do with derivative. It's nothing else than topology. The image of the compact is compact, and therefore its supremum is in the set. So if it's in the image, it is reached by it has a pre-image at the source. That's precisely what I'm saying. Now, I said, well, f is differentiable. That's not saying much. It's differentiable at this point C, because I know that this point cannot be at the boundary. What is f prime of C? Well, let's go back to the definition of the derivative. The one that we all know, even from calculus 1. This is the limit of f of C plus h minus f of C divided by h when h tends to 0. Okay, let's look at the quantity f of C plus h minus f of C divided by h. So here, the limit has to be taken for any value of h tending to 0. Whenever it's positive or negative, it should be the same. So it should be the same as the limit when h tends to 0, h positive, and it should be the same if I were to take the limit as h tends to 0, but h negative. Here, I still haven't said anything deep if you see carefully. I mean, the definition of limit does not allow me to restrict one direction. I can't look only at the limit on the left or on the right. Actually, you could do that for a function depending upon one variable, but for a function depending on more than one variable, you need to define a directional limit. This is something crazy. So here, let's say it is better definitively not to impose any order in the limit. So it could oscillate about 0 or tends to 0 by positive value or tends by 0 by negative value whatsoever, as long as h tends to 0. Okay. Now let's look at this quantity. When h is positive, so the denominator is positive. So the sign of this quantity is definitively depending upon what we have on the numerator. What do we have in the numerator? F of C plus H. F of C plus H is always less or equal than F of C. Why is that so? Because F of C is the max of F, the supremum, but also the max of F as X belonging to AB. So if I take another value, it cannot be bigger. So it has to be like this. So this quantity is less or equal than 0. For H, positive. Now, let me erase this. What about for H negative? When h negative, the denominator now is negative. And the numerator is still negative for the same reason, whatever the value of h. For all h such that c plus h belong to AB actually. We don't even need to take, so let me write it better here. For all h such that c plus h belongs to AB, f of c plus h is never bigger than f of c. So this is still true. So this quantity is a ratio of two quantities. One is non-positive, this is non-positive. Yes, so this has to be non-negative. Alright, now let's take the limit of this quantity when h tends to 0, h positive. Remember, if you take, you can discretize this if you want, but if you take a function which is always negative and you look at the limit at a specific value, well, the limit cannot be positive. So the limit of this quantity remains less or equal than 0. Now, this is one of the exercises I've discussed with you when we were talking about limits. If a sequence is always positive, its limit cannot be negative. Well, you can discretize hn here, then you have, so you can take a sequence hn tending to 0, hn positive. So maybe let's do it. So limit when n tends to 0, n tends to infinity, all the hn being positive. Well, you have a sequence here now of a sequence of real numbers which are always non-positive. The limit stays non-positive. Same thing here. If you can discretize this, although it's not necessary, you can look. I mean, what I said about sequence was also true about function. Huh? This quantity, this is a sequence of real numbers which is never negative. The limit will never be negative. Although those two limits should be the same, but one tells me that it should be non-negative and the other one tell me that it should be non-positive. Well, the only possibility is that this limit, as n tends to infinity, therefore, is equal to 0, and this is f prime of c. And this ends the proof of Rolle theorem. All right. So here you see, you may complain, says, yeah, but you discretize. Yeah, but I discretize, but you know what? I'm using the following thing. F of x tends to f of x naught if x. So I would say something like this. A function f of h tends to f of tends to a limit L when h tends to 0 if for all sequence hn such that hn tends to 0, f of hn tends to L. So I mean this property is something that, it is true we haven't discussed much, but this is something that is a direct consequence from the, let's say, the consideration we have in topology. I mean, you can easily prove this thing. It's not so hard. And I don't think that is something that will bother you much. All right, so this ends the proof of this theorem, the Rolle theorem. So again, realize one thing is that the heart of this the heart of the proof of this theorem doesn't come from any fancy consideration concerning the notion of derivative. Not at all. No. I just just saying that if you have a sequence of function tending to something, and we know that this function is always positive, the limit must be positive. Same thing if a sequence of if a function tends to something converges when h tends to 0, and the function is never negative, is never positive. Well, then the limit should not be negative. I mean, the sign should always remain the same. That's what I'm saying, even when you take the limit. That's pretty much what I'm saying. All right, so a direct consequence of Rolle's theorem is, as you know, guys, the mean value theorem, and I'm pretty sure that you know also how to go from Rolle's theorem to the mean value theorem, but let me show you for sake of consistency. So, mean value theorem, so it's actually a monument in analysis, but it's unfair. It's unfair not to mention Rolle in this. Not to mention Rolle in this theorem, because Rolle theorem is really the heart of this theorem. This is only actually a very easy corollary of that Rolle theorem. Okay, so the setting is like this. Assume that you have a function f from AB, an interval to R, continuous again, f differentiable on AB again, so pretty much the same setting as before. But now I don't assume anything on the value of f at A and B, but the conclusion looks like a generalization of Rolle theorem. Actually, it is. No? There exists a C belonging to the interval AB. That is a C bigger than A less than B, such that f of B minus f of A equal f prime of C times B minus A. Well, that's why we call it the mean value theorem. So it tells me that the average rate of growth between, because I can read this like that as well. This is perfectly equivalent to saying f of B minus f of A divided by B minus A equal f prime of C. It tells me that if I look at the average rate of growth of f between the 2 points A and B, well, this average rate of growth is reached by the derivative of the point in between. So the thing we have in mind is pretty much this thing. So suppose that we have A here, B there, and this is f of A, this is f of B. I've drawn the picture in the case where f is, let's say, more or less, not exactly, but let's say is globally increasing, I'll say, but it doesn't need to. Well, you see that the slope here is mimicked by this derivative, by this slope, and this slope at least have 3 points here. 1 is enough, of course. Again, there's no unicity in this point. Proof of this theorem. Well, the proof is easy, once we know Rolle theorem, of course. Let's consider g of x as being equal. So here I improvise a bit, but it's not so much hard. F of x minus a divided by b minus a times, what do I need? I need to have an f of something. So I need to have an f of b if I'm correct. Hold on, I need to check. So no, that's not that. It is f of a minus f of b. So let's say f of b minus f of a, but plus a sign like this. I think this should be the right thing to be. No, there's a minus sign. Sorry, I think so. Hold on, give me a minute. I should not have improvised. I know that I should not have done this. This is a silly thing from me. What I want to have is g of a. Well, g of a here in this case it's f of a. But I want g of b to be also equal f of a. That's what I need. So if I put g of b here, I have 1. No, that's correct. That's fine. No, that's fine. That's the correct one. Oof. Right. So let's consider this function. I claim that this function satisfies all the hypotheses of Rolle theorem. G is continuous on AB. Why? Because f is continuous on AB, and this is a defined, or let's say, what is it? A linear map, so it's actually as smooth as you want. So there's no problem with this part here. So it is impartably continuous. The sum of two continuous functions is continuous. G is differentiable on AB. Why is that so? This part is differentiable anywhere you say, and f is differentiable on AB. So the sum of two, or linear combination of two functions which are differentiable on the same interval, on the corresponding interval. Now, as I said in my drive, what is g of a? G of a is f of a, and because when I replace x by a, you have 0. And I look at g of b. Here you have a b minus a instead of x minus a. The b minus a and on the top and the one in the bottom cancel out. I got f of b minus f of b minus f of a. So this f of a. So g of a equal g of b equal f of a. We don't need to know that. So therefore it tells me that there exists a C from Rolle theorem such that g prime of C equals 0. Yeah, but what does it mean that we have a point point C such that g prime of C equals 0? That means that g prime of C equals 0 equal f prime of C. So by let's say by using simply the rule for differentiation, the linear combination of a derivative is the derivative of the linear combination. So this is minus the derivative of this. But what is the derivative of this? We have a constant here, which is f of b minus f of a divided by b minus a, and the derivative times the derivative of x, so that's a constant, sorry, times the derivative of minus x minus a, which is minus 1, so this is what we get. And of course this is equal to 0, so that tells me exactly that f of b minus f of a equal f prime of c times b minus a. Or, in other words, pretty much what I said earlier. This is equal this. This is the same, of course. So observe one thing, so that to go from Rolle to the mean value theorem, it's quite elementary. It's just that what you have to do, you see, I was not even prepared for that. I should have been, maybe. It's just subtracting the function to this function, subtracting let's say a linear function, and then just verify that Rolle theorem is valid. And that's quite, let's say, a easy step. So it's a bit unfair that we always talk about the mean value theorem and we don't mention Rolle in this theorem. That's why it's not always wise to give names to theorem, which is a bit unfair. Alright, so this theorem, the mean value theorem, before I like to talk about, let's say, things that are related to the real line, I would like to tell you something which is true, and I'm not going to prove it because it's not the context of this chapter, is the following thing. Assume that f is defined on an interval AB and take its range in Rn this time. So it makes sense to talk about the derivative of f at a point t. Well, this is nothing else than a vector this time. F prime, f1 prime of t, f2 prime of t, fn prime of t. Now the problem is that the mean value theorem won't be true, or the role theorem won't be true any longer. You won't have the following thing: f of b minus f of a will be equal to the derivative of c, the derivative of f at a point c, times b minus a. So here in this case I need to put the b minus a in front of, because this is a scalar, these are real numbers, and f are vectors here. Indeed, I should actually put something like this to emphasize that it is a vector. Although this writing wouldn't make sense because we have a vector here in the n-dimensional space, we have a vector here in n-dimensional space, right? And we have a scalar here, so it makes sense. But the problem is that this is simply not true. Simply look at the example of the parameterization of the circle. Let's take phi of t equal cosinus theta, cosinus t, sinus t. Well, I'm going to tell you something that I hope is not going to surprise you. Phi of 2 pi minus phi of 0 equals 0. So if this theorem will hold, it would mean that there will exist a c in the interval 0 to pi, such that phi prime of t, let's put this like this, equals 0. So c, if phi prime of c equals 0, that is minus sinus c cosinus c. Well, we know it's impossible because the sum of the square of those two guys is always equal to 1. So it cannot be both vanishing. So this theorem is definitively not true when the goal of the function you consider is multidimensional. So this is not true. However, there are one thing which is true. Is you can take a norm in Rn. So any norm in Rn, so you can take, for example, the Euclidean norm in Rn. So that is the sum of the square of the square root of the sum of the square of the component. The b minus a, well, since b is bigger than a, I leave it like this. I want to replace it by the norm of f prime of c. Well, if I do this, it's still not true, but it gets closer. I think there's one thing, indeed, what you can say is this. You can take the supremum of the norm of this vector over t when t goes from a to b. But the price you have to pay is an inequality. So surprisingly, this theorem has, we can say, two things. We use this theorem almost every day in analysis, much more than the mean value theorem we have seen earlier. And we still call it the mean value theorem, abusingly, which we say the generalized mean value theorem. Also, the proof of this theorem is not trivial, and you need to know a lot. You need to know a lot. You need to be smart when doing those estimates. And pretty much the proof consists of proving the following thing: that this quantity is less than is satisfied with, let's say, m times epsilon, and for all epsilon positive. That's actually one way I can prove this, is to show that this inequality holds for all epsilon positive. So if it's true for all epsilon positive, it's going to be true for when you remove epsilon, because those quantities should not depend upon the choice of epsilon. Okay, so this was just a remark I wanted to tell you. Unfortunately, this is not in the frame of the context of this model. All right, so now let's talk about theorems that you know also, but that are deduced from the mean value theorem. So I like to put them as an exercise because I don't want to spend time on this. This is quite clear. Assuming that f defined on an interval AB. So again, the range in R continues on AB, differentiable on AB, and f prime of x is identically equal to 0 on AB. So even if f is not differentiable AB, well, the conclusion is that f is equal to a constant. And actually, I can tell you what constant is. F coincides with f of A, which is equal to f of B, here in this case. Well, proof, exercise 3, use mean value theorem, and it follows immediately. Another exercise, which also I don't want to let's say to develop too much because it's almost easy. And the same assumption as above, so f of f defined from AB continues on AB, differentiable on AB. So most of the time it's differentiable in everywhere. I mean, we just take an interval and most of the time the function is differentiable any way you say. Assume that f prime of x is positive on AB and f of t2 is always bigger than f of t1 if A is less or equal than t1, less than t2, less than b. So in other words, if the derivative is positive on an interval, the function should be increasing on that interval completely. Observe one thing. I will discuss about a lemma in a minute, where I will show that if at a specific point the derivative is positive, then what I will be able to show is that the function is increasing, but only in a small interval nearby this point. Here there's no notion of vicinity at all. As long as you know that the derivative is positive everywhere, you get this thing, even if t1 and t2 are far from one another. Right, and of course you got the same thing if you replace f prime of x on AB, then f of t2 is less than f of t1 as long as t1 and t2 are, of course, in the interval, otherwise I don't see the point. Actually, you could remove the strict inequality by a large inequality. This is also true, obviously. Alright, so I leave those things as exercise. They are quite elementary. Just again, proof. I like to say direct use MVT, and it follows absolutely immediately. So let me now I'm going to talk about things which are not going to be, so I'm going to state a lemma. I won't need the lemma for myself, but you will need the lemma, because I'm going to state a theorem afterwards, which is a part of your assignment. So I won't be proving everything, in other words, that's what I'm saying. So let's first of all state the lemma. So assume f is defined on an open set U in R, f is differentiable, and let's say A belongs to U, right? And let me state this lemma into two parts. Assume f prime of A is positive. f prime of A is positive. Then there exists let me state it like this. Then there exists H0 positive such that for any H that satisfy this, that is H between minus H0 and plus H0, F is increasing. No, I do not need this, so I take it back. What I need is F of A plus H is bigger than F of A if H is positive, and F of A plus H is less than F of A if H is negative. So I take it back. I'm not saying that F is necessarily increasing on that interval, but let's say we can compare F of A and F of A plus H, whether H is positive or negative, and essentially it is dictated by the derivative of F of A. Exactly, so I say positive, sorry, I forgot this. Assume exactly the opposite. So my A is not very nice, I must confess. Right? Well, what I'm going to say is pretty much the opposite. Then there exists H0 positive such that for all H less than H0, meaning this of course, well, F of A plus H will be less at this time than F of A if H is positive, and F of A plus H will be bigger than F of A, if H is negative. Well, you know what, you believe me or not, if you can prove one of these, you can prove the other, right? Actually, if the only thing you have to do, once you have done a proof for one of each, you just replace F by minus F, and you got, of course, exactly the inequality in different sense. But for the sake of making sure that you will be in good track to prove this lemma, I'm going to prove this part, which I claim is a little bit more subtle, or just a little bit more subtle than this one. All right? All right, so proof of this lemma in this case. Well, the proof follows directly from the writing of the fact that F is differentiable at A. So only of this, huh? Please do the other one as an exercise. So F is differentiable, badly writing, F is differentiable at A implies that F of A plus H equal F of A plus H F times F prime of A plus H epsilon H. I hope you all agree with me where epsilon H tends to 0 as H tends to 0. So here I don't say whether H is positive or not, but this is the thing. Now, saying that F prime is negative, meaning that I can rewrite this entire thing like this. F of A plus H equal F of A minus H times the absolute value of F prime of A, and you know what, for sake of simplicity, I don't want to carry out F prime of A at each time, so I've said F prime of A equal minus L and L is positive. So minus L times H plus epsilon H. All right. Since L is positive, I claim that there exists an and epsilon H tends to 0 as H tends to 0. Well, what does it mean, this? This means, so let me erase that part. By using the notion of limits, the definition of limits, it means that there exists H0 positive such that if H is less than H0 but bigger than minus H0, so in other words, the absolute value of H is less than H0, epsilon H is less than L, in modulus, L divided by 2. Yes. So in other words, what I'm saying is that for all epsilon positive, there exists an H0, a delta, which is now, it stands for H0, such that if H minus 0 is less than delta in absolute value, then epsilon H is less than epsilon, divided by 2. Well, okay, well, so I just took in the definition of the limit, the epsilon, nothing to do with this one, pay attention. The definition of epsilon, I took epsilon equal L divided by 2. Alright, so this is the only thing I said. Alright, so this means that upstairs, what do I have here? Epsilon H is in modulus less than L divided by 2. Alright, so now let's look at this thing. F of A plus H equal therefore F of A minus H times L plus epsilon H. Which means what? Which means that we have this. All right. So now what do? We have to look at each cases. Let's look at the case where H is positive. What happened? If we need to know what is the sign of A plus H minus F of A. That's what we need to know. The only thing we need to know. If it is, so what do we need to know? So let me make a draw because I'm not so sure if yeah, right. When H is positive, we need to show that this quantity is negative for H less than H0. What is the sign of this? Well, the sign of this is equal to minus the sign of H times L plus epsilon H. Now I need to erase something upstairs here. Well, okay, so the sign of the product is the product of the sign. Well, since H was positive, the sign of this object, so let me rewrite this again, this is not nicely done. Since H is positive, the sign of this thing is just the sign of this guy. L plus epsilon H, sorry. Because H is positive. The sign doesn't change. But what is the sign of L plus epsilon? So L plus epsilon H, I claim this is bigger than L divided by 2. Why? Because epsilon H in modulus is less than divided by 2. So in other words, you have epsilon H is confined between L divided by 2 and minus L divided by 2 from this inequality here. Well, add L on both sides. it tells you that L plus epsilon h is bigger than L minus L divided by 2, that is L divided by 2. So this quantity here is positive again. But we have a minus sign here, so this means the sign here is negative. Which means exactly what we wanted to have. The function to be, let's say, some sort of decreasing. So the image of f of a plus h, where f of a is here, should be less than that of f of a. Now, if h is negative this time, well, we still have the same thing. What is the sign of this? Is still the sign, it is still minus the sign of h, of h times L plus epsilon h. Same thing, but this time, so L plus epsilon h is positive this time, still doesn't change, but h is negative, so the sign here is negative, and since I have a negative sign, it becomes now a positive sign. So this means pretty much what we wanted to have. If we take h negative, f of a plus h is bigger than f of a here in this case when h is negative. So this ends the proof of this lemma, at least in the part where the derivative of f was negative. Well, if the derivative of f is positive, it is pretty much the same thing. All right. Now let me state the theorem, and you will need this lemma to prove it. So in other words, I'm implicitly telling you, please prove the theorem I'm going to state. And it's actually, it is exercise 7 from the section, from the which section? From this module, so from the chapter 4 in Rosenlicht, and the theorem tells you this. Yeah, so I might not formulate this in the same way they formulate this in the book, but it doesn't matter. So let f define on A, B, take its range in R, and assume that an f is differentiable on the interval AB. Again, it might not be exactly formulated that way in the book. It doesn't really matter. Assume there exists a C, D, let's say a C could be equal to A and D could be equal to B in the case where F happens to be differentiable A and B at the same time. But let's say I want to avoid this. Assume that we have two numbers, a C and D, such that this hold. With so assume C, D are, assume, oh, I should write it better. Assume there exists C less than D such that A less than C less than D less than B, so I'm repeating a bit myself, it doesn't matter, such that f prime of C equal, say, M, f prime of D equal, so let's call it M1 and M2. Right. So then show that, we'll say that for any, for all little m belonging to, so here's the trick, in belonging to the interval m1, m2, if m1 is less than m2, or m2, m1 if m2 is less than m1. So I might use this notation, you see. So I mean, it's a point between those two real numbers. So definitively I want m1 different than m2. So which one is the biggest? I don't know. It doesn't matter. It could be this one bigger than this one or vice versa, I don't care. But I'm telling you, for any value in between those two numbers, whatever the order is, so I like to summarize this for all n in m1 and 2, and I put a double arrow on the top to tell you that it depends which order you take. I mean, whichever sense it makes, in other words. For all m in between, there exists a C not C, sorry. There exists alpha belonging to the interval CD such that f prime of C equal m. So what does this theorem say, in other words, because I formulate this theorem in a quite complicated way. It says that if you have 2 points in your set, which could be A and B if you want to, I don't care, such that f prime at this point is a certain value, let's say very negative, for example. You have another value which is extremely positive, let's say 100, where it tells you that between C and D, f prime will take all the value between that value and this value. So in other words, you could say that this theorem is the intermediate value theorem for first derivative. Well, that's also something quite surprising. The first time I saw this theorem, I could not even believe it. Why? Because f is maybe differentiable. F prime, again, remember I told you, has no reason at all to be continuous. No way. You've seen the function I mentioned before, x times sinus of 1 over x squared. This function is what did I say here? Yeah, so no need of this. You take this guy. You take x squared sinus of 1 over x. This function is continuous everywhere, differentiable everywhere, even at the origin. Right? But the derivative is highly discontinuous near 0. Well, I mean, if the first derivative is not continuous, I cannot use the intermediate value theorem as I've learned before. That if I have a value here and a value there, then you have to take all the value in between. Again, f prime here, the key thing, the key ingredient, the key reminder, I should say, the warning is that f prime is not necessarily continuous. This is the main thing. But the nice thing is, and again, it's going to be, I'm telling you, it's written in the book actually, you have to use actually the classical intermediate theorem for continuous function and not for first derivative. It has nothing to do with the derivative, but about the function, the intermediate value theorem of the function f itself. And again, Rolle theorem. So just to show you that actually under those information, there is Rolle which itself was deduced from a topological argument in the first place. So it reveals that without topology, we are not capable of doing anything in what we call geometry. Geometry by means of computing derivatives. That's pretty much the idea of geometry we have nowadays. I mean, so without topology, we are completely lost in computing derivatives. Pretty much, that's what it says. All right. So this exercise is a part of your assignment. You have some hint in the book, so I think I will leave those hints like this. It says use the intermediate value theorem for f and Rolle theorem. Yes, I think that's quite enough as a hint. If you need help, of course, I'll be happy to. All right, now to finish this video, I'd like to finish this video by stating a lemma which could drive me to speak about L'Hopital's rule. But L'Hopital's rule is a nice theorem, for sure. It's absolutely beautiful. But it's not really used, indeed. And it's overused by many people. And it has also the danger is that we think that we can use it in higher dimension, and it's not the case unless you are somehow lucky. So it is what I like to call, a hammer to kill a fly. Most of the time, I use other expression, which I don't know if I could say that, but yeah, it's pretty much using hard stuff to do, let's say, little thing. However, there is nice thing in the proof of L'Hopital's rule, which we gonna be using for proving the Taylor formula for a function f. So I prefer to. So I'm gonna state this lemma now, and I'm gonna skip the proof in the next video, and I will talk. We'll talk about the Taylor expansion also in the next video. All right. So lemma. So it's going to be like this. Assume so let B be positive, and both two functions f and g are continuous on minus b. Oh, well, okay, we can do it like this if I want. And differentiable on, well, pay attention here, we have minus b, 0, union 0, b. So in other words, it's a little bit different than in the former case. I allow the function to be continuous pretty much everywhere, right? But the differentiability is not only at the boundary, but also I don't necessarily expect the differentiability to be true at the origin. Well, for Taylor expansion, actually, it will be at 0, but I just want to be more differentiable. That's not nicely written. That's better. That's nice. Assume also that g of x is never equal to 0, except at z. So I should say, well, something like this. G of 0 equals 0. Actually, I also want to have f to be equal to at 0, but g of x different than 0 for x different than 0. All right? Then, conclusion is like this. For all x belonging to minus b, 0, union 0, b, there exists an x1. So here, again, I would like to use the notation I have taken before, belonging to the interval 0x, meaning x1 is between x and 0 strictly if x is negative, or x1 is less than x but positive if x is positive. So this is what this notation means. I could have set up the lemma only, let's say, on that part of the interval, but I didn't want to make any restriction. So this is what this notation here means. so I'm not finished. For any x in this guy, I claim that the ratio between f of x and g of x coincide with f prime of x1, g prime of x1. As an exercise, once I've shown you the lemma, as an exercise, a corollary, I would like to say state L'Hopital's rule. I like to say at 0 because there was also L'Hopital's rule at infinity. So there is actually 4 L'Hopital's rule when you have an indeterminate form of the form 0 divided by 0 at 0, 0 divided by 0 at infinity, infinity divided by infinity at infinity, and infinity divided by infinity at 0. That's 4 different ways. But let's say it's at 0 when the ratio looks like 0 divided by 0 and not infinity divided by infinity, and prove it. And let's say elaborate a proof. Using this lemma. Actually, maybe I can tell you how this will help. If you do not know what the limit of f of x of f of x and g of x when x tends to 0, here it's not clear because you see both function f and g are continuous. The limit for x tending to 0 tends to 0, this tends to 0, we do not know. We can't determine the limit. We have to work more. Right. This is something that is quite clear. Now it tells you, this lemma says, well, but for any x you take, there exists an x1. So between x and 0, in other words. That's pretty much what it says. Such that, well, this one is the same as this one. And now, if the limit of those guys exist, so if in other words, if this x1, let's say, is in the domain where this limit makes sense, well, this means that this guy here is pretty much, if this guy admits a limit when x1 tends to 0 for obvious reason that you do not know of, then you will say that the limit of f of x and g of x will be this guy. So that's pretty much what L'Hopital says in this form of its statement. Again, so there is 4 different ways you can formulate L'Hopital. Again, I want to say I'm not a big fan of L'Hopital's, even if it's a French mathematician. It does not, I'm not necessarily super patriot because of that, definitively not. That's one thing I want to say. And also because we barely use it. And when we have to use it, there are, fine example where you really need this to compute limits. There are quite extreme cases where logarithmic and trigonometric function are mixed together or something, or you are really in presence of functions which are impossible. But let's say typically most of the time we never have any problem and we don't need much this theorem. So I won't insist much on L'Hopital, but I like this lemma because it will be of use for proving the Taylor expansion. Alright, so we'll see this in the next thing.